Good afternoon, everyone. We are very pleased today to receive Roberto Fernandes. He will talk about the SCUBES Project, IFS-like work with S+. Roberto is professor at the Federal University of Santa Catarina. He got his PhD in Cambridge, UK, in 1995. He was postdoc at URGS, Johns Hopkins, has Gemini Fellow, and he also has spent several times in the Instituto de Astrofísica de Andalucía in Granada, Spain. And as much of you should know, he is responsible for the development of the Starlight code that's very used everywhere in in the synthesis of stellar populations all around. Sid, go ahead.
Thank you, Laerte. So, okay, let's get started. And I'll get started. Can someone switch off that light, please? Done. Much better. Now we can sleep in peace. Okay. Yes. 2, 3. Okay. All right, let's get started then. Thanks very much for the invitation. And in case you're wondering what this is, probably not going to have time to explain to you, so let me just start with the ends. That's a good question for the end, okay? Just ask me what that is. So this is what I'll be talking about, the SCUBES project, which is doing integral field spectroscopy work with 12 photometric bands, the 12S plus bands. And this is a project I'm coordinating, and these are the young people around which are helping me, Julia, Amanda, Fabio not so young anymore, Eduardo, Mayara, and Victor Hugo. Julia and Victor Hugo are my current students. Victor is here, spending this month here with me. And there's also that lady over there, which you might recognize. So the idea, what is the idea? What do we want to do here? The idea is really inspired in this work we published last year in the monthly notice with Julia and many people from the S+ collaboration, where we show that with 12 bands of S+, we can do these exquisite photometric fits. You are seeing a spectra there in the background, but don't look at it. Just look at the 12 bands, and there's an observation, a photospectrum, and a fit to it. And this is a fit of stellar population. It also accounts for emission lines. And that's that galaxy over there. And this is the fit of one spectrum per galaxy. And here in the bottom, we have several IFU-like products. Here we have stellar populations of young, intermediate age, and old of a cube produced with S+, that is the 12 images. Emission lines separating nitrogen from H alpha, which is really a miracle because there is only one filter for them. And this is a zoom in into the central region, which is very similar to a MUSE proper integral field spectroscopy map of the same galaxy. So we were very excited with this, saying, okay, can we do this for more galaxies, for many more galaxies? That's the idea of the SCUBES project. Okay, that this first pilot study was very promising. So let's see if we can do it for more objects and covering, of course, a much larger area, which is good for environmental work, for environment work. So we have a homogeneous data set, which is a big advantage, despite the limitations, of course, only 12 bands, not real spectroscopy. We cover the full galaxy, so the whole galaxy, whereas a typical IFU covers an arc minute. And the filters, as this paper shows, they are good for both stellar population work and also emission lines. So let's see if we can explore this for many more galaxies. So the idea here is to first to produce a pipeline which will allow anyone to extract data cubes from S+ in an organized manner. And then after that, we also provide a database of cubes with some preprocessed material. And the preprocessing will be a good part of this talk, I'm afraid. They're very boring, but very relevant results when it comes to analyzing the data. And then in the third part, I'm going to explore a bit the data cubes that we obtain, producing maps of stellar population properties, emission lines, radio profiles. We'll also see if I can find the time. I'll tell you a little bit about a project which combines S+ with Muse spectra and data-driven approaches. So let's get started. There will be plenty of slides here. See the time well there? No, just counting my time here. Okay. So, okay. Let's present to the tool. There will be just one slide on it, really. It's the work of Eduardo Lacerda, mostly inspired on the work that Fabio did and others before him. This is the diagram for the flow diagram of the code. Basically, the user asks the scubes.py, I want the data cube of this object, and it goes to the S++ data, calibrates the images, and gets you back a fits file with all you need, all the fluxes in the 12 bands, the errors, and plus metadata that you can work with. Okay, the code is 99.9% ready. The documentation is also nearly ready. This is going to be distributed to the S+ collaboration and elsewhere pretty soon. So once you get the data cube, you can start playing with it. So you can plot your images. These are the 12 images for this early type galaxy, which we call S0001, just for simplicity. Is some galaxy in the Fornax cluster, most likely. So here we have log flux in ergs per second per square centimeter per angstrom per pixel. This is one example. This is a Nejon spiral. You see here the 12 bands of S+ again, from the near UV to the Z band. You can plot the same thing in a different way. If you're more a fan of magnitudes per square second, you can use this plots here for an irregular galaxy, well, as a spiral galaxy, really, with some irregularities. And here are the images of the errors in magnitudes as well. You can see here in each of these little frames here, you see a number. This number is the PSF, not in arc seconds, but in pixels. Remember, the S+ has a pixel of 0.55 arc seconds. So the thing here is typically 1 point something. Okay, this is important information because we'll have to homogenize it eventually. When you do the proper analysis, you have to homogenize the PSF, among other pre-processing steps. Another galaxy, again from the U band to the Z band, and its errors. So you can do, this is the first exploration. I just use the tool itself, extracted a cube, and having a first look at the data. Apart from the tool itself, we plan to distribute a pipeline. Oops, sorry. Not a pipeline, but the database, which will eventually look like this, just a web page, a table, where you're going to go to this galaxy, click over there, and there'll be a series of plots and diagnostics of the quality of the data, the sort of color maps and stuff. I'll be showing you a few examples in a minute. And Mayara Sampaio is in charge of that. We're starting with an initial sample just to play with of about 350 galaxies, mostly from Fornax, Hydra, Antlia clusters, and but also trying to make a special sample of big southern galaxies that will be good for IFU-like studies. So we have this initial sample. We'll be seeing plenty of pictures of this initial sample here. So once you have the data, you have your maps, you can start playing with it. And here are some RGB composites. You have 12 bands. So we have 12 bands. You have, I don't know, what's the combination of 12 3x3. You can do many combinations of filters here. Here's one combining H alpha with the R and G filters. This one is H alpha is a 6600 filter, which is narrow and centered in H alpha and nitrogen. So you can see when it's red here, you have H2 regions there as well. So that's the H alpha filter. This is spiral, galaxy. So each combination shows you different things. This one, for instance, is something which the green and blue channels reflect more or less the D4000. I'm not sure you know what the D4000 is. At 4,000 angstroms, there is a kind of a discontinuity. The spectrum jumps from one high level to a low level if you have old populations, but it remains essentially flat if it is young populations. So you can use combinations of filters which on top, on one side and the other side of the band of 4,000 angstroms to give you an idea of the stellar populations and combine that with something else. And you can do many other combinations. Here are 9 other combinations that Julia was playing with. Those previous ones were examples from Ayara. So there are many different combinations which highlight different things. That depends on what you want to see. Okay? And these are traditional combinations of filters in the sense that I combine the flux with one band, with another band, and another band. But you can look at it with different eyes, different mathematical eyes, and look at these things as points in a hyperspace of 12 dimensions and project them in principal components, project them using t-SNE and other, compression algorithms to explore this material. If I have time in the end, I'll show you some experiments we're doing with that as well. Here's our favorite galaxy. We wish every one of them looked like this. Unfortunately, this is the prettiest one so far. It's NGC 1365 in the Ford cluster. Okay, the other thing you can do is to use the so-called tree filter method. The tree filter method is really just a way of using that narrow band which encompasses H alpha and nitrogen, plus the 2 broad bands around it to estimate H alpha flux. And that's what Amanda Lopez has been doing in La Plata. So this is basically an H alpha map of this galaxy. This is another one for a more irregular galaxy. So the information is there. It's just a matter of how to extract it, how to use it to suit your goals. In this case, she's interested in line emission. What is going on? Is the sound okay? Sounds a bit odd. Well, I'll keep talking. Okay. Other sorts of analysis you can do. This is all first exploration of the raw data cubes. You can do structure maps, which highlight structures in your images, like for instance this shells around this early type galaxy. There are several tricks on imaging processing tricks. This is always the raw data cube, but there's one thing that anyone who has worked with an image or with an IFU data cube knows that we have to get rid of things that we don't want, like stars which are between ourselves and the galaxy, or other kind of stuff that contaminates the image. So, and this is not always simple to do. The tool itself that Eduardo developed does that using Sextractor, but Julia Tainá has developed an alternative version of this masking algorithm, so I'm going to show you a few results. She initially starts with a big cube. The galaxy is only there, but she uses a big area around the galaxy to identify things which are not the galaxy itself. Uses this to map them and mask them out, and then in the end we make a smaller cube for our analysis. So this is very handy if you want to do the analysis. This is going to be distributed, I think, in your database. I'm not so sure yet. I have to negotiate that, because this is a value-added product, right? So this is not something which comes from the data. It's a value-added product. Subtracted what? This is just mask. Just mask. It's mask. It's mask. Mask, not subtracted. Automatically. I think now it is fully automatic, but in the beginning it did require some interaction. Sometimes it's even in a. You have to be careful with it. Always inspect the final result, but the version we have now is fully automatic, and it's working fine. Of the 50 galaxies I've been playing with, only one has a mask which should be improved slightly. So here, more examples of the mask. We have a mask for the galaxy itself, for the stars, and whatever is not stars or galaxies is called sky. Okay, and having a sky mask is very useful for some tests that I'm going to be mentioning in a few minutes. Sometimes they look weird because, yeah, the universe is not always the way you want it to be. There's a star next to this galaxy which eats up this part, and here is are the spikes of a star which is outside the frame here, but which is eating up this end of the image. But this is the useful area. Where is my mouse? This is the useful area for work. Okay, the examples of the mask. Preprocessing number 2, that will involve some filtering and PSF homogenization. The filtering we're going to be using is inspired by the work of our late John Steiner. We started applying this Butterworth filter in this Gemini data cube, and we found that it to be quite useful here in S+ as well. So what we do, starting from our original cube, this is an average of all the bands, but you can think of it for a single band. So here's an image, the original one, with the masks. Then we apply a Butterworth filter, which is a filter in the Fourier space. You basically turn this thing into Fourier space and cut whatever is high frequency. Already you can see the color map is always from -1 to 2 here in this log scale in all frames. So you already get much darker here, which means it suppresses quite a bit of the noise. If whatever you say. But the word filter, we homogenize the PSF, which basically is the usual trick. You figure out which of the 12 bands has the worst PSF, and you make them all compatible, right? Which is a further degree of smoothing. So you see it improves substantially the image. Here you have a signal to noise map, the average signal to noise over the whole 12 bands. And it's really remarkable, this effect. You can look at this in this different way. This is a map of what I call sigma 4. I just go to a pixel, draw a circle of 4 pixels in radius, and compute the standard deviation. Okay, just that. And this is the original one. Of course, you're not supposed to look at the galaxy itself. Here, this doesn't mean anything in the galaxy itself. It means it would be like a structure map of the galaxy. But what we want to look at is at the sky. You see how the sky gets much brighter, much fainter, or much darker as you go from original to the Butterworth and then the final PSF convolved image. The noise is basically suppressed by a factor of 5, 6, even 7 sometimes. So it's good to have these are useful pre-processing steps. Okay. Another example, just compare how much darker this is here. Wherever you see white here is because it's negative. I'm taking the log of a negative number, so it should be negative in many regions in the sky. On average, the sky should be 0, so this is good. Except you're going to see very soon that it's not as 0 as we would like it to be. That's another further pre-processing step I'm going to be mentioning very soon. So another one, you see how much darker it gets. So useful pre-processing steps. Okay, improving the data, getting rid of some of the unwanted characteristics here are RGB maps on different combinations with the filters before and after we do the filtering. Okay, it looks much prettier. Another one of a interacting system. Again, the preprocessed cube looking much better than the original. And not much magic doing here, kind of straightforward, all right? Okay, oops, what, go back. I just mentioned to you that the sky is not as zero as we would like it to be, and we noticed it recently. Well, we've been noticing it for a while, but only recently we readdressed this issue. And the problem is that imperfection in the subtraction of the sky, which is done in the original data calibration, they can lead to spurious effects. Crazy things like an elliptical galaxy where the outskirts are surrounded by what looks like young stars and youngest dusty stellar populations. We start getting weird stellar population results in the outskirts of elliptical galaxies, and that signal that there's something is not well. It's not, and we figure this is to do with some residual sky. So, and we came up with a local correction which improves it. So let me see if I can show you what the problem is. Here, what is in black here is the region that we are analyzing. What's supposed to be the sky after some sigma clipping and standard steps, right? So, and what we're plotting here in these gray lines are the spectra of all these black pixels here. And on average, they are slightly positive and blue. The very low flux levels, you cannot see it from the scale here, but it's very low flux level. But it's on average slightly blue and slightly positive. And this looks, if you think of it as a stellar population, I'm sorry, this is not real spectrum, right? It's not wavelength, just the band from 0 to 11 or 1 to 12 if you prefer. But it's actual wavelength just growing in that direction. So, and here again, another galaxy, and for every galaxy we look at, there's always a small residual positive spectrum in the sky, and that's not good, right? Because that looks like young stellar population, young and dusty stellar population, when it's just garbage. So, to deal with that, here I have another example. It's a bit hard to see it in practice. Just look at this. This is a map just of the distance to the nucleus of this galaxy, right? Just the distance. So red is really far away, well outside what we call the galaxy contour, and blue is in the middle. And here are the main spectra along these regions. And as we go to the outside, down here, you see that the mean spectra becomes, this red, this dashed curve here, this dotted dashed curve, which is the mean spectrum which we evaluated from a sky frame. So the problem is really not here because this is too far out, but these spectra here, which are in green and yellow, they are affected. So this would lead us to believe that in this outer part of this galaxy there is something which is bluish and which is good, well fitted with a young and dusty population, which is just not there, right? So what we came up with, okay, let's subtract this mean spectrum here, and at least maybe we'll be able to recover these spectra which are close to the edge of this galaxy. And it okay, just following orders. Okay, much better now. Do I sound like I don't know, some singer? Okay. Okay, so this trick improves the analysis of the outer part of the galaxy. It doesn't affect so much the middle part, but the outer parts it improves a bit. And the final pre-processing step, I told you, will be boring, but it's necessary to do some decent analysis of the galaxies, of the data itself, is to bin. why to bin? You have to group spaxels so that we have enough signal. That's, again, mostly for the outer parts, not for the middle ones, which have enough signal. And this spatial binning, there are several ways of doing it. The classical one is to use the Voronoi tessellation. Like Michele Capellari has a very famous code for that, which is a standard technique with a few caveats. One of the caveats, Julia Tainá, my student, she's in Spain now. One of the caveats is she's analyzing an image of M101, which is enormous, and it would take her about a month and a half of processing just to get the Voronoi binning. When the images are very large, then you have a problem. Our images, some are large, the others are not problematic. But the one she's analyzing is just a nightmare. She has to figure out other ways of doing it. Another alternative is to just bin things along ellipses. That's pretty good for early type galaxies, but not for spirals. So let's see. This, whoever has ever used the Voronoi Capellari's Vorbin code, this is a standard plot that it uses. It makes these Voronoi zones over there. In the middle, there are many smaller ones. Let me just go to this map, which is perhaps more illustrative. So it segments, it makes a segmentation map, really. Each of these different colors here is one group of pixels, which is compact altogether. And when you add up the data within this group of pixels, you improve your signal to noise. That's the idea. You have to improve the signal to noise. Then you have to tell the code, I want the signal to noise to be 50, 100, 10, whatever. You have to tell the target signal to noise code. And we work on a signal to noise which is based on the blue bands because they are very important for cellular population work. So we combine them into a super filter and do the signal, do the Voronoi binning there. Here we're binning it to trying to reach 50 of signal to noise in these blue bands, and here you're trying to reach 100. You see they get much larger, the zones. So it, it kind of distort maybe hopelessly the galaxy, but for some purposes it's still useful. If you want to do some, just find global scale gradients, that's good enough. This is the same thing for actual IFU data, by the way, right? It's not because it's photometry, the IFUs are just like that as well. So here's maps of the signal to noise, etc., etc. Here's an example of the same galaxy after this before and after binning the Voronoi, with Voronoi. You can see that you lose resolution in the outer parts, but it's still good enough if you want to measure a global gradient of age gradients or metallistic gradients or stuff like that. But there are lots of tricks involved here. One of them is that you say, I want a signal to noise of 50, and you run your code, and it says, okay, here your signal to noise is now 50. You group them this way, it's 50, and it's usually not. Well, I know this from this paper 10 years ago, 11 years ago. I did this all with a CALIFA, proper IFS work, and we aimed for one signal to noise. We did apply the Voronoi code, and it didn't reach actually the desired signal to noise. We knew that because we had spectra, we could check it. Here with photometry it's tricky, but just warning that there are several tricks in this business. The recipe is easy to use, but if you actually reach the desired signal to noise or not, that's a different story. There are several tests you can do to check that. Another alternative, which is reasonable when you have round galaxies like this or elliptical galaxies, is to bin things along ellipses. And here are the spectra that you get from the inner ellipse, and then as you move further out. These are all ellipses. These are the mean spectra along these ellipses, which are all pretty good looking. There's no obvious problem here. When you do an ellipse like that, of course, the statistic also helps a lot because you have many spaxels, many more spaxels than in a compact Voronoi zone. And that helps you with that sky issue that I mentioned before. You cannot see, but maybe you can see in this one. Here's another example. Well, you probably cannot see. And the fact that you cannot see it is good. What you cannot see here is that there are two lines here. One is the data is in color, but there's a faint gray line in the background, which runs right on top of the data, which is the spectral fit, which I'm going to be explaining it to you in a minute with my stellar population code. So only here in the outer parts, you get some deviation from the model and the data. So this is a good alternative for these galaxies. And since this will be, 50% of the sample, maybe more because we're working with clusters and there are plenty of these galaxies in clusters, this might be good alternative. It's a bit depressing that you take so much care of the 2D images, all that filtering, etc., and in the end you collapse your galaxy to a radial, a 1D, right? When you do radial profiles, it's really all 1D. But it's very useful anyway, especially for galaxies. These are not truly 2D, right? They're so symmetric that they're actually one-dimensional intrinsically. So after all this pre-processing, there must come some post-processing, of course. So I hope I haven't bored you too much with all these steps, but this is how work goes, right? You spend a lot of time in the not so interesting parts. So I'll now show you some initial results of applying our all-star code, which is a spectral synthesis code tailored for photometry. You can combine photometry, spectroscopy, other things, but this one is applied only to the S+ photometry. Okay, so these are things which I have been doing this last month here at IAG. So here's the first example. We have several. This is an elliptical galaxy. The first, I think, it's not the first I showed you. One of the ones I showed you before. An elliptical galaxy. Or here you have a map of the log of the mean stellar population age. I'm not sure you can read it, but that's 10 over there and 8 down here. So that's 10 giga-years, and that would be 100 million years in black. And you can see it's very old in the middle, with some slight variation perhaps in the age here. And apparently young in the outskirts, but not true. That's a side effect of the effect I mentioned before, which you have not fully corrected. Here, when it's dark, means that there is basically no dust. Again, that's an elliptical galaxy, no surprise there. It's all consistent. This is how many solar masses per square kiloparsec you have. Because I'm fitting stellar populations, I know how to convert light to solar luminosity to solar masses. This, too, is one of the miracles that the code does. It has the flux of H alpha, and it's equivalent to width as well. The flux in H alpha alone, remember, I have 12 bands only. One of them contains H alpha and nitrogen, but I'm managing to somehow separate nitrogen from H alpha. That's a different seminar. That's the paper that I mentioned in the beginning. We figured a way of separating the two in a semi-empirical way, which works pretty well. So this is H alpha flux. You might say, this is an elliptical galaxy. What are you looking at? H alpha in emission. But it is. And the equivalent widths are here in black, you can see. This is 0.6. This is about 3 angstroms, 3, 4 angstroms. This is typical of a retired galaxy. So very weak equivalent widths. So this is all looking consistent, except for the outer parts. The outer parts look, maybe you should not analyze these galaxies as far as we're trying here. And this initial map here kind of already told us that. I haven't mentioned this before. But what this is telling me is that my fits are dark, meaning very small residual, percentage residual, right? That's model compared to data. A few percent, 1, 2, 3% here in the middle, but up to 20% residuals in the outer parts. That's not a good fit at all. And that's because we have not managed to I mean, it's noisier, and we have not managed to subtract the sky correctly, perhaps. So this outer part over here is when we should not be analyzing. And this is a way of showing you that. Here in this top panel, you have a spectrum of the central spaxel. Very good. This is a spectrum of a spaxum which is somewhere over here. Okay, it's noisy, but you know the error bars are there reflecting the noise, so it's not so bad. But this one, it was spaxel there, right at the edge over there. It's that red dot over there. So this is really useless. This is really useless. The error bars are telling you this is useless, and the stellar populations we are getting are weird. Okay, so this is what this is telling me is that we should not really go beyond a few, into this red ring here. This is already too bad. We should concentrate on the inner parts where you can get reliable results. Another example here of a spiral galaxy. Actually, it's a spiral, but it's not it's a early typish because it doesn't have much dust. Yeah, I know it doesn't have much dust, both because of the images, and because I don't find any dust in the middle. Here are the ages. H alpha, very little emission, and the equivalent widths are very weak. And again, the fits are very bad in the edges. Again, okay, you shouldn't be going. So the real message here is that this outer contour is a bit too optimistic. You just cannot analyze the data there in a spaxel by spaxel basis. Maybe with some ringing, elliptical rings, or some other kind of spatial binning. But the inner parts are good. Another one, this is a dust spiral. You can see it in the image itself. And there we find a lot of dust along the disk. Plenty of star formation as well. You can see by the dark colors here in the middle, which reflect young ages, which you can also see because of this H alpha emission over here. You see the H alpha map is matching what you see in the. This is an H alpha flux. This is an H alpha filter, so it's not the same thing. And last one, this looks a bit messy, but it's a beautiful image, in fact, because you can see the H alpha flux and the terms very clearly. When you see dark here, you're seeing the young stellar populations. You see a lot of dust in the middle. There is a lot of dust in this galaxy. This is being observed by Muse. We compared it to it, and it's very compatible. Of course, there are regions here we should not be looking at. Over there, for instance, you see the fit residuals are large, and over there. So in the end, we're probably going to have to define another mask which tells, okay, we analyze this big part here, but maybe you can only trust this inner part, right? This is in process. So again, I mentioned to you that it's a bit depressing that you all collapse things into when you do radial profiles and you do a radial analysis. It's a bit depressing that you work with the 2D, you take all care of filtering all this stuff, and then you compress your galaxy to 1D by doing radial profiles. But it's not only us. Everyone who does IFU, proper IFU, does that. And that's simply because it's much easier to do it. This is an example of a paper of mine back in the CALIFA days. MaNGA is the same thing. Muse is the same thing. So these are luminosity, extinction, age, metallicity, surface mass, star formation rate, all of these light profiles along the radius. We are collapsing the galaxy into 1D. Okay? I'm about to do this for S+. Just want to warn you that everybody does that, even for proper integral field spectroscopy. And so this will be the surface brightness profile. That converted into solar masses per square kiloparsec. That will be the age. You see a few ups and downs over here, but it's all old, all between, I don't know, it's 5 or 4 and 9 gigayears. So it's the mean age of the stellar population, weighted in some way, which I may explain to you later. This is pretty much flat, except for this outer being here, which may have a little problem. Very little dust as well. If you look at the value 0.1 magnitudes, that's all very reasonable. The equivalent widths are all very low. Another one. So radial profiles is probably the way to go, especially if you want to do a statistical analysis. Okay. I will now mention you another type of work that you can do with S+ data, which is to combine it with some other kind of data. In this particular case, Muse. This is the work that is being led by Saskia Schlagenhauf, who's a visitor from ARMA Observatory. She's German, as the name implies, but she's also working she's doing her PhD in Northern Ireland with Mark Sarzi. And this is Vitor Hugo Sarce, my student who's here. What they're trying to do here is to combine Muse data, which is that monster over there, with S+ data. I think S+ would fit into one of these units here. I don't know. So this is a monster. This is not a monster. This is 8 meters. This is 10 times smaller in radius and 100 times smaller in area. Except that this one is much better for something than the big monster. The big monster is a fabulous IFS, but it does not reach the 4,000 angstroms region. I mentioned in the beginning that the region around 4,000 angstroms is very informative. There is that 4,000 angstroms break. There are high order Balmer lines. There are all sorts of stuff that happens there. 500 angstroms around 4,000 are worth much more than 3,000 angstroms in the red. there's more information per angstrom in the blue than in the red. And Muse does not reach that. Muse starts at 4,800, 4,850 angstroms more or less. So that means that its stellar population work, it's okay, you can have a spectrum, but it doesn't reach the most informative part. Whereas S plus has 6 filters covering this part. So can we combine the two things? The idea would be here to take an image or data cube really with S plus, combine it with the Muse pointings. Muse is fabulous, but it's a 1 arc minute only. So this galaxy was observed with 2 pointings, and the data here, and half of this pointing is really nearly useless, but the other part is good. So to combine these two things, maybe you can. We're not sure yet. We're going to call it SCUBES, but SCUBES with Muse will be an SCUBES. I don't know. So Victor and Saskia were working on putting these things together. It's it's a messy work, and oops. So, and here's an example of the sort of things that you can do. What you're looking at here, you have these little squares. These are the S plus photometry. Okay, there are 12 points over here. There is a black line in the background which you can hardly see, but there is a black line there, and that's the Muse spectrum. It starts somewhere around over here. That's the Muse spectrum. Part of it is painted in yellow. When there are either emission lines or some noisy sky regions, we painted it in yellow. But the rest is black. And the reason you cannot see the black is because there is a blue line there, which runs really from 0 to infinity, because it's a model. And that's a model that we get by fitting simultaneously the photometry, the S plus photometry, and the Muse spectrum. We're fitting both things at the same time. So that's a more complete analysis than fitting either of those separately. Fitting only the Muse part would be okay, but you would miss this very informative region here. Here you see the 4,001 angstroms break, which I mentioned before. Of course, we did not cover it with the detail of spectroscopy with S+, but it's very well covered with the photometry. And you can see that this model is matching quite well both data sets. If you want more details about this, Victor can explain it to you. Here you have a zoom in of to see the details of the spectral fit. It's really exquisite, angstrom by angstrom fit. And the main result here of this analysis is really this plot over here, which tells you basically it's the star formation history. How many stars, how many solar masses have you been converting per unit time from the Big Bang to here? So you're here in time, okay? The past to the present. So 1 million, 10 million, 10 giga-years ago. And what you see here are 2 cumulative curves, which tell you that basically this region, this whole region here, is really very old. There's some star formation from 10 giga-years up to a few giga-years ago. And then most of the light comes from this old population, maybe a few % of these younger populations over here. But in mass, most of the stars are really old. And that's really the question that they are trying to address here, because they're trying to compare that with other analyses in Muse. That particular galaxy looks old in the outskirts and younger in the middle. So it's a bit stranger than the usual. Usually it's the other way around. So this is an example of, if this works, we can do it for many more galaxies. Complement Muse with the blue part. You know, there is an instrument planned by ESO, which is the blue Muse, which is really try to do Muse by covering this important part. And the reason for that is this. It's very informative. This blue region is very good for stellar populations. Have very good age indicators. How am I doing for time? Since I have a few minutes still, let me just show you this initial slide that I showed you before. We have done this before in the Julia's paper for NGC 1365, which is the southern hemisphere, S+ data. This is J+ data now, is the twin in the northern hemisphere. And what she's doing here is taking an image of M51. This is a beautiful pair of galaxies here. And since from our dust maps, we analyze it pixel by pixel or in Voronoi zones if necessary. We have the dust map that we derive from that analysis. You just undust the galaxy, you just undo the extinction correction, just put a plus sign or there is a minus. And basically here, this is what the galaxy will look like without dust. Right? Just one of the few games that you can play with the applying the inversion, the map of the extinction that we obtain from analyzing this observed data cube. You can look at what it would look like without dust. And you see this whole dusty region over there covering this neighbor galaxy. It goes away. You see the extinction is really working. The extinction correction is working really well. You can see all these features here which are attributed to dust. They're all cleaned up now. Just an example of the things that you can do with this sort of analysis. Marcus, for some reason, doesn't believe it, but you can ask it in a minute. So just really to conclude, this is already, I didn't think I would have time to reach here. I mentioned data-driven approaches to exploring this data. This is, I showed you many pretty color maps combining fluxes the way astronomers did for centuries. Just, blue filter in the blue filter, the green, the red. You can put H alpha, other combinations. But there are other ways of looking at this highly dimensional space. Just think of a spectrum as a point in the 12-dimensional space. It's a vector of 12 components. And you can look at it with different tools. I tried one. I saw a seminar by a student of Rama. Elvis was his name. Is he here? No, anyway. And he talked about this T-SNE technique, which has a horrible name. I don't know, T-distributed, stochastic, blah, 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 blah. It just, pick a vector of many dimensions and compresses it to less by similarity. Just, is this vector similar to this one in this high dimensional space? And what I did was just, just pick this data cube from S+ and compress this 12-dimensional data space to 3. And these are the 3 maps that it identifies. What does that mean? Well, now you can use your astrophysicist's eye to see, well, there's the bar region. The numbers here, they mean nothing, right? They mean this new projection. They don't have a physical meaning. But they're telling you that these are star-forming regions along the arms. There's an old population in the bar, and probably some star formation there as well. And these 2 other components kind of complement each other. And then I put them all together in a red, green, and blue, and I produced this monster here. It's not very pretty, but it was a very quick and dirty exercise. Just a way of exploring the data in a data-driven way, really. The data is drawing that map, not me. Okay, and of course there are other ways of doing this, and inspired by John Steiner again. This beautiful sentence in his famous 2009 paper that says that talking about PCA tomography. It's saying that in the traditional scientific method, one formulates a question and looks the data for answers. Whereas the principal component analysis gives you an answer. It's an objective one. It's a mathematical one. The problem is to figure out what the question was, right? So it's a different way of working with data cubes, and it's a pioneering work. And these are old results. I have done this. Julia has done this in her master, but these are the slides I found. These are experiments I did. It's not S+ data, it's J+, but it's totally equivalent. And this is just a map. Oh, let me show you a prettier one, perhaps. This is a M101, and the red, green, and blue channels here, they are not filter 1 or filter 2 or filter 3. They are principal components, which are each of them combinations of all the different filters, and whose meaning, God knows what they mean. But that's the trick. The advantage of PCA tomography is that you may not know the meaning of each eigencomponent, but when you look at the image, then you can start, attributing, doing a reverse engineering and saying, that's what that means. So blue here, whatever this eigenspectrum is, it's mapping star formation along the arms. And maybe the difference between blue and this violet, which mixes with red, has to do with extinction. because the dust is more to one side or the other. You know, there are many different games you can do with that. Really pretty. But I really didn't plan to go this far. So let me leave you with this last slide here. So our next steps, we have to refine our samples. The whole pipeline needs a few touches here and there. We have to define in practice what is the outer radius we can work with as plus data. An optical beating scheme, and then when this is all done, just press enter and have fun. That's about it. Thanks a lot. Thanks a lot.
Questions to Sid?
Sid, suppose you are looking at a nearby galaxy, really nearby, something like Magellanic Clouds or M31, and then you decide to identify binaries, not by nebular spectrum, but intrinsic accretion disk spectrum. Can you do that and separate from H2 regions?
Not sure I understand the question.
Yeah, suppose you have a resolved or quasi-resolved population, and you have to decide if you have an H2 region or binary. The binaries, they produce a different emission spectrum, and not talking about nebular emission binaries, but intrinsic accretion disks, and then you decide to separate this from the H2 regions. Do you think that's possible using SCUBES?
We would have to see if you can adapt a trick that I use to separate nitrogen H-alpha here.
Yes. Yes.
So the trick that I used, that Julia used in her paper last year, is based on the fact that we can get a very accurate equivalent wave of H-alpha plus nitrogen with that filter. It's very accurate.
All right.
And in galaxies, this number pretty much tells you if you are a star-forming galaxy or an AGN or a retired galaxy. That number helps you tell which side of the BPT diagram you are. So once you know that, okay, I'm going to do my analysis forgetting liners, only talking about, forgetting AGN, only talking about star-forming galaxies. That helps us limit the scope of the problem. Maybe if there is some sort of empirical guide in the case of binaries versus H2 regions, then that could be applied. But you have to adapt this idea.
Right. Okay. Okay. The second question is regarding this cleaning. How can you do that without three-dimensional information? Because you have regions that are affected by dust, and they are progressively affected.
And that's a problem of stellar astronomy coming to extragalactic seminars. Of course, it is three-dimensional, but the way we model it, we go to a spectral here. We say there is stars, and there is a screen of dust.
Okay, you simplify the thing. Yeah.
Is a simplified.
Yeah.
We actually do little bit more complicated, but it's all parameterized. You know, we say, okay, if there are young stars, there may be some more dust than normal.
Yeah.
But it's really.
So you apply the full dust distinction to the region.
Yes,
okay. Okay.
yes.
Right.
It is.
Okay. Thank you.
More questions, Betty?
You're not asking about magnetic fields, for God's sake.
Of course not. Sid, eu ia perguntar em português, não, melhor because this is. There has been a lot of surveys currently surveying circumgalactic gas, right? This is pretty fashioned in the sense that, okay, in different wavelengths, we want to know what's going on in the surroundings of the galaxies to understand better the feedback, the mechanisms of feedback, and the influence of this circumgalactic gas on the evolution of the galaxy itself, and so on and so forth. And your survey is able to catch these outer regions as well, right?
Yes. Go on.
So you are in the boundary, let's say. Did you have any chance to get a sample of objects and see how these, how your results fit or compare with these circumgalaxy surveys?
So
for
the second question, no, not yet. But there is the point that you're making is something that Claudia raised my attention to, and maybe we'll try this, is to see if we can find the gas that we can map here is H alpha.
right?
Right.
Yeah, because you have dust
We have
as well.
we have a filter around H alpha, etc. So that's the one we can map.
Mhm.
In individual galaxies, it will be hard to go into a halo regime, but it's probably possible to do a stacking kind of work. We stack many images or many profiles with again, you have to gather signal because it's a weak emission outside. So the stacking analysis may be promising. I think there was a student here a couple of years ago or something which thought about this. So stacking, you may be able to detect an H alpha halo if there is one. That's all I can say. And someone in the collaboration is going to look at that.
Right. Yeah, because
That's
this
something
is
that Claudia just mentioned to me a couple of weeks ago.
right. Okay.
Questions? No more questions. Let's thank Sid again.
Let's do a coffee break last.
Tá ali em cima.